Hi everyone. So today, as I promised you in the previous video, we would be looking at PEFT. So if you guys don't know about PEFT, you guys need to go and watch my previous video in which I have talked about LLM evaluation metrics. In that, I give you a very basic definition of what actually PEFT is. And in this video, we would be looking at a lot of things. I will give you a very small example. I will give you the resources from where you can go and study about PEFT in detail. So let's start. So introduction to the LLM part, we have already discussed like GPT, T5 and BERT are based on transformer architecture and have benchmarks in various NLP tasks. Now beyond NLP, they are expanding into other realms like computer vision with VIT, stable diffusion, layout LM and audio domains. When we come to the traditional approaches to LLMs, they are the prevailing models involves extensive pre-training on broad web scale data. So this is actually followed by the fine tuning on specific downstream tasks. Don't worry, we will be looking at fine tuning, like how you can actually use an existing model and train it on your data. Even though we have done the similar thing in TensorFlow Hub, we extracted a model from TensorFlow Hub, we trained it on our data and then used it for our purposes. Now, challenges is with scaling and fine tuning. So as the large languages model are very big in size, full fine tuning on consumer grade hardware becomes unmanageable. In my system, I don't have any pre-built GPU. So if I have to do, I usually use my university's devices for doing machine learning, or either I go to Google Colab, or the third option is using Microsoft Azure virtual machines for the same. Now, storing and deploying individual fine-tuned models for every task is very costly, as I told you, especially, given the models are so large, they have billions of parameters. Now, when we come to PEFT, PEFT is parameter efficient fine-tuning. It's a library, it's a module that was released by Hugging Face in the year 2023 beginning. The talks about it have started in 2022 and all the details were out. So PEFT is designed to tackle the challenges in LLMs. Instead of fine tuning the entire model, we can actually focus on a limited number of parameters on which we need to train the model. Now, it reduces both computational and storage demands. It also sidesteps the problem of catastrophic forgetting. A phenomena in which that is observed during the LLM fine tuning. So PEFT has a lot of advantages, a lot, believe me. So the storage benefits, as I already told you. For instance, while the big science, the dataset the model that we are going to use is the MT0 large by big science, and you can go and read in detail how this whole model works. It's a text generation model. It's if you want to use it, here you go. You have all the code available. You can go and play with it. Even though I would recommend you to directly go and play with it, you can use the small version or the base version because obviously it's large. And even you have one MT0 XXL model. Now that is, just imagine if large is so big, then how would be double XL? So the model occupies 40 GB. Its fine tuning would result into separate 40 GB checkpoints for each task. So in contrast, the PEFT checkpoint for each datasets are just a few MB, and yet the performance on the power will full fine tune. So these lightweight trained weights from the parameter efficient fine tuning are simply appended to the pre-trained LLMs. So this will enable the same large language model that you were using previously to cater to various tasks. This eliminates the need to swipe out the entire model and start from the very base. So we will look at all the 4 tasks. We will look at LoRa, we will look at prefix tuning, prompt tuning, T-tuning. Now, I will give you a very brief example or definition of all these 4 tasks. But in today's video, we would be focusing on LoRa. So what is LoRa? It's a low rank adaptation of large language models. If you want to read the research paper, I have given you the link to the research paper. You can go and read. I will just redirect you to here. Yeah, this is the research paper. Till the point it loads, I will give you a brief, tell you what exactly it is. Just imagine you have a whole big model. Imagine of this MT0 large. Now, obviously, it would have billions of parameters. It would have so many things. And if you go and read here, the fine-tuned model, you have small, base, large, XL, double XL, then you have LB1, LB7. So yeah, we are using it has 1.2 billion parameters. Just imagine. Now, suppose you want to fine-tune it. So obviously you would want it to, not take that much computational space or time and storage. So what can you do? Using LoRa, you can actually compress it to much lower things. So like using LoRa, you would be able to scale it down to a much smaller size, much smaller computational power would be required for it, and a lot of advantages you get. I know it sounds a bit tricky, or things that are not usually used in the beginning of LLM training, but yes, it is very important part. So here, if I go, yes, fine tuning steps 25,000. Then you have fine tuning tokens, that is 4.62 billion, and it is present in B float 60. So pretty big, obviously. Now it is still loading. Cool. So till the point, I will tell you the other 3 points also. Prefix tuning. So this, you can think it is a prompt tuning that can be comparable to the fine tuning universally across all the scales and tasks. I would expect that you guys actually know about what is actually a prompt when it comes to LLM. So yeah. So when it comes to prompt tuning, the power of scale for parameter efficient tuning also starts. Then you come to P tuning. GPT understands too. Yeah. So in detail, we will study about each of them in detail in the coming videos. But in today's video, as I told you, we are focusing on LoRa. So yeah, it's still not loaded. So when it comes to LoRa, this is a very important website, tuners, and it has this LoRa configuration. So a fine tuning a model with LoRa. It has all the things, PEFT type, auto mapping, revision, everything. Cool. So we'll start with it. So I'll give you the link to this notebook in the description section as usual. You guys can go and play with it. Okay. So let's consider the case of fine tuning a big science empty zero large using LoRa. Now, one thing is pretty sure, we can't fine tune the whole model. Like obviously it has 4.6 billion parameters. How can we? Now for that, first of all, we are installing the necessary Python libraries. PEFT is a library that provides an implementation of the PEFT method, so which we will use later. We are also installing the transformer library with the state-of-art transformer models and the dataset library for loading and pre-processing data. Next, we're importing these essential classes. Auto model sequence to sequence LM is a class for the transformer library that that allows us to work with sequence to sequence language models. Now from the PEFT library, we are importing the get PEFT model, and we are also getting a LoRa configure part that we will be using. Now we also have task type classes to configure our model. So this is a model, model name. I will just run it. Big science. Then we are defining a print trainable parameters model. It prints the number of trainable parameters that in our model has. It takes all of them, parameters in parameter, and yeah. Okay, it got disconnected. I will just reconnect it to make sure things work. Cool. So I will just run it. Yeah. And then we have PEFT configuration. Now, when it comes to, so the research table is loaded. So let's have a look at it. And then we can again move back to the code part, because LoRa configuration start exactly from here. So if you read this research paper, you can see our parameterization. We only train A and B, pre-train weights, and then you're applying PEFT on it, and things can actually scale down. Now, if you read this research paper, you will get to know a lot of mathematical functions. I know it can be hard. If you guys want, I can actually, make a video of this simplifying a lot of things. So this is the batch size, sequence length, fine tuning using LoRa. So these are the results that were, connected, got using sharing with adapters, and same it goes. So this whole research paper works on that. Now you have the trainable parameters of these models, the raw base, then you have LoRa applied to it. You have got 0.8 million parameters for it. So you guys can actually see how effective it is. So I will give the link to you of this research paper through the notebook only. So you guys can go and have a look at it. So here we have set the name, and in the stipend we have defined the utility function, this called print trainable parameters. So this function take model as input and calculates the total number of parameters in the model, as well as the number of trainable parameters. Now if it then prints out these numbers, which can be useful for understanding the size and capacity of the whole model, because we need it. Now we have PEFT configure, that in which we are putting LoRa configure, and then we have task type. Okay, when we are creating configurations for a PEFT model using the LoRa configuration class, we specify the task type as sequence to sequence language model. Now the reason we are using that is because the model that we are using, big science MT0 large, is a sequence to sequence large language model. Now that's the reason we are defining it here. Then we have inference mode, that is false here. Then we have R, LoRa alpha, and LoRa dropout. Now, coming to these parts, we also set different hyperparameters such as R, LoRa alpha, LoRa dropout, which controls the behavioral and structure of the PEFT model. I will take you here, and then you can look at every part. You have base model name, then you have task type, and then you have inference mode, that is Boolean, then you have R. So this is the LoRa attention dimension. Then you have the target modules that you can actually tell the LoRa model, the LoRa configuration part, that the names of the modules to apply LoRa to. You don't necessarily have to apply it to all. That's your choice. Then you have LoRa alpha, the alpha parameter for LoRa scaling, obviously. Then you have dropout value, the dropout probability for the LoRa layers. If you guys have seen my TensorFlow videos, you know what exactly is the dropout layers. Then you have fan in, fan out. So set this to true if the layer 2 replace store weights like fan in, fan out. For example, GPT uses convolutional 1D layer which stores weights like, and then hence you should set this to true. We don't need it right now. Then you have the bias, and then you have modules to save. So a list of modules apart from LoRa layers to be set as trainable and saved in the final checkpoint. Then you have layers to transform. So it indexes to transform. If this argument is specified, it will apply the LoRa transformation on the layer LoRa index. Cool. So we have set it everything. Now we will wrapping the base using Hugging Face transformer model by calling the get PEFT model. So I will just run this, and most probably it will just download the whole model here, and then it will print the trainable parameters. Now coming to the part, it is taking a bit of time. Cool. So we have the model X, then we have the get PEFT model, then you have the model, and we are putting it inside the it. So you guys have already seen in the big signs here how many parameters it had. I think it had 4.7 billion something. We will go down, and yeah, we had 4.6 tokens for that. Now when it comes to parameters, you can actually go and actually see here the parameters for large is 1.2 billion. That's a lot. So the parameters function would here obviously print the 1.2 billion parameters, and all are trainable. That would give us 100%. Yeah, here you go, 1.2 billion, and then you have all parameters, the trainable parameters, so it's 100%. Now inside this I have set LoRa alpha 32, 0.1, and for that I will get model PEFT configuration, model X. I have defined it, and it will give me a parameter of 0.19. So that's 0.19%. Just think, you have actually scaled down the model so much. You are only using 20, I think, what would you say this? Yeah, I think it's 22 million, 35, yeah, 23 million. Cool. So it's using 23 million parameters out of 1.2 billion parameters. So that's a big scale down, you are only training 0.19%. So that's cool. We can actually change things here. Let's set LoRa alpha is equal to, let's say 40. What's about this? You can actually train it, and let's do this, and let's see what is the result this time. This will obviously return me the same thing. I shouldn't have run that, and then that's it. The rest of the training loop remains same. So when you are ready for this particular model, you can just go to the inference and save the model. You simply model.save pre-trained, and just the output directory where you have to save it. Now I want you guys to go and do it with a lot of other models that are present here. You can simply go here, text to text generation, and then you can look at a lot of models here, and if you want, you can even do that with other models like the image classification, the image segmentation, a lot of models, text classification, then you have token classification. Guys can do it according to yourself. So yeah, here we go. So now it's 0.16%. So it has reduced a bit. But if I change it, like if I do it, let's say 26, 27, and let's keep that 8 only, and I will just make changes. So obviously this time the results would be different. Yeah, it's doing 0.19 again. So this is how things work out. If you want, you can do it 0.9, and results would not be different because we are doing that for LoRa dropout layer. Why would it be different? So that's it. You guys can go and actually look at how these functions are working. The LoRa attention dimension, as I already told you. Then you have bias, LoRa patterns, layers to transformation, a lot of things. So yeah, when you are playing with this notebook, make sure when you are running code, you here in task type, put the task that is actually desktop. You don't do things like you are putting a different task model inside this PEFT configuration, because obviously it won't work then. So yes, now I would recommend you guys to go and play with this notebook also, that is of official Hugging Face, fine tuning large models using PEFT adapters, transformation, bits and bytes. It's a wonderful notebook. You guys would learn a lot about it. Like, they are loading a opt 6.7 billion parameters model, and its weight are in half precision float 16 and are about 13 GB on the hub. So if we load them in 8 GB, they would require around 7 GB memory. So they are actually even scaled down in the bit part also, from float 16 to float 8. So that's wonderful. And then they are post-processing the model. They are applying LoRa on it, and the total parameters are 0.12. And this is just next level part that they have did here. Obviously, I think in the parameters part they have made some changes. So they are post-processing on the 8-bit model. And then for LoRa, they defined here, RE16 LoRa alpha 32, and that they have some target modules here. Then they have the task is casual language model, and then bias is none. Cool. And then they can train it, share adapters on the Hugging Face hub. Then you upload adapters from the hub. So yeah, a lot of things. I would give the link to this notebook also in the description section, and you guys can go and download it from there and play with it. So yeah, that was it from my side in this video. I hope you guys get exactly what is LoRa. In the next video, we would be talking about prefix tuning, prompt tuning and p-tuning. And you guys can comment out what exactly you guys want next, and I would make a video on that. So yeah, thank you and have a nice day.